Right. Good afternoon. Right. Thank you for coming to this talk. What we lack in quantity, we're going to make up in quality. I'm Maurice Naftalin, as you see, and today what I'm going to talk about is the nominal topic is about complexity, but it's about program performance in general. So I'll talk quite a lot about complexity, and I'll talk about some other stuff as well. We've got a 2-hour slot. This is the first time I've done this material, so I'm not sure how long it'll take, but I'm sure it won't take 2 hours. I'm absolutely determined to take a break in the middle, so if I haven't stopped by after an hour, tell me to stop. But nobody can concentrate for all that time. So because I'm used to giving conference talks, I start off by introducing myself, and actually it's kind of worth doing that on this occasion, because the background to this talk is I wrote a book about, or I wrote half a book about Java 5 many years ago, because obviously Java 5 is many years ago, and the great thing about writing books, I've written another book as well, and I'm doing the same thing, and I'm doing the same thing with this book as well. The great thing about writing books is you get a chance to talk about them. Well, you go to conferences and you talk about them, and you get a chance to talk about them twice. So the first time you talk about what a great book you've written, and the second time you talk about all the mistakes you made in this book and how you mean to put them right in the second edition. Well, I haven't got a second edition, but I'm going to talk about some things that didn't exactly get wrong in the generics book, but or in the collections half of the generics book, because you can see it says Java generics and collections. So I actually wrote the collections part. The generics part is what makes it famous, because there are loads of books on collections. But what I wrote in there is stuff that, as you'll see, it gave me an interest in collections, which I haven't lost, and I'm going to one of the things I discovered stuff about them which now we need to update, and there's things I wrote in there we need to update because machines have changed a lot, even in the 10 years since that was written. So there's other stuff about me which doesn't matter. Right, so this talk is usually, or sometimes entitled, Not Your Father's Complexity, which is a kind of, I changed that because it's an idiom in English, which people, native English speakers understand, because what it means is basically it's not if you say not your father's anything, that means that it's not the thing that you grew up being used to. Right? It's not how it used to be. So everybody understands that in English, but I'm afraid it doesn't probably translate very well. So what was your father's complexity? Well, I guess most people here will know. The idea was that you would get a model of program performance which depended on essentially on the number of instructions that are executed. So that's what lies behind it. The idea is that of course we don't really care in a way how many instructions a program executes. What we care about is how long it takes to execute. But that's really complicated and difficult to calculate. We're going to find it's actually got even more complicated and difficult than it used to be. And so so we have a proxy for that, which means we have got something that we count instead of we can calculate. Instead of calculating how long it's going to take, we calculate the number of instructions it's going to execute. And that's what the big O algorithmic time complexity is about. It's so-called time complexity, but it's actually the number of instructions complexity. Now that needs to change because, well, I'll talk about whether it ever worked and about why it needs to change now. So a reasonable question to ask is, if it's not your father's complexity, like, who is your father? Well, your father is this guy. Professionally speaking, obviously, I'm not casting doubt on your parentage. So the name that's most associated with complexity is Don Knuth. Is a giant figure in our subject, creator of tech, Turing Award laureate, etc., 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 and also author of The Art of Computer Programming, a multi-volume work which was actually foundational. It really set the way that people thought about programming for an entire generation. For my generation, that was the text, and Knuth developed the science of algorithmic complexity to a very high degree. So he was, I mean, it was there as a mathematical concept already, but he applied it to program, he applied it to program analysis. So since I'm going to talk about why we shouldn't be paying any attention to that, why we need to change our attitude to it, I do want to say something that really needs to be emphasized at the start of any talk, which is going to discuss program performance. So Knuth actually said something really sensible here, which we don't pay nearly enough attention to even now. And you don't even need to worry about the first paragraph. The takeaway is we should forget about small efficiencies about 97% of the time. So he was the person who first said that premature optimization is the source of all evil, which again is again may not translate into another language. The original quote is that love of money is the root of all evil. But for programmers, it's premature optimization. So people, when they're writing their programs, instead of thinking about writing them to be maintainable, writing them to be in good style, writing them so that they'll be readable, writing them so that they'll be able to, so they'll be easily enhanced, instead they think about how are they going to run fast. This is almost always, it's always a mistake to think about before you're actually running your program. Programmers turn out to have very poor intuition about where the critical sections of code, the performance critical sections of code are in their applications. It's extremely difficult to get them to develop an intuition for this. Only through measurement can you find out. And until you know you have a performance problem, you shouldn't be trying to optimize. So what I'm going to say for all the rest of this talk is only interesting 3% of the time. So that always needs to be said. That said, everybody loves to talk about performance, and that's like it interests everybody. Here I am talking about performance, even though and I talk about performance much more than 3% of the time. So there you go. So Knuth was the guy who really brought computational complexity to the foreground of our understanding of how programs run. What is it and why should we care? Well, it's the mathematical definition looks a bit off-putting, but it's actually not very hard. So if you've got an algorithm that is going to execute, that you assign a time complexity, say order g of n to it, then it's going to complete that provides you an upper bound for how many program steps there's going to be. You may need to calculate g of n. You may need to multiply g of n by some constant, but given the right constant and a sufficiently large n, a sufficiently large data set, you can this gives you an upper bound to how many steps the program is going to take to execute. So the diagram is sort of reasonably helpful here. You don't know how many steps your program is going to require. It's f of n, and it's some some function which may be quite hard to calculate. But if you can find a g of n, which multiplied by some constant, will always be more than f of n is above some limit, then you at least you know the worst case for the execution time of your algorithm. So Knuth, for example, I mean, like you saw the opening slide, the title. The calculations in the art of computer programming are really complicated. They're really complicated, and the derivations are very hard. But here's a sample, right? For multiple list insertion sort, if you've got m lists and each list is of length n, then the number of steps that Knuth calculated was going to need to be executed was 3.5n squared plus 24.5n plus 4n plus n plus 2. So like if you wanted to know how long your program was going to take to execute, you might think you were going to have to work that out, but that's actually really not very important, because if n is big, then you don't care about any of the terms except n squared, because that's going to come to dominate. And just for the sake of having something to do this, and I thought I can do it in Java now. So basically what I'm going to do is, all I'm doing here is I'm just comparing the actual formula that Knuth calculated for multi-list insertion sort, 3.5 n squared plus 24.5 times n plus 4 times n plus 2. And I'm just going to compare that with, I've just chosen some kind of arbitrary constant to multiply n squared by, because this is an algorithm of order n squared. We're not going to care. The point is that although this is actually the precise number of steps it's going to take, we're not going to care about that because we believe that it's going to dominate, that the n squared term is going to dominate if it's sufficiently large. So if I type compare for some kind of ridiculously small numbers, then it's going to print out the result of the formula, and it's going to print out the result of 4n squared. And you can see that 4n squared is the 16 is obviously much less than 73. But if I make these values a bit bigger, we could have, I suppose, something more realistic. Say we've got 3 lists and we're going to say 10 elements. We now find that the n squared is catching up. 4n squared is catching up on the precise value. And if I actually start to do something remotely realistic, then you find that already now it's pulled ahead. And the larger n becomes, the more dominant the n squared term is going to be. So if I do it for a bigger number, then you'll find that that's clearly that the n squared term dominates, and we can throw away the rest of the information. A precise value isn't important. If what we want is an upper bound to the number of program execution steps, then this is how we get it. So that's most of the demonstrations you're going to have today. Well, unfortunately, program performance measurements don't really I've discovered they don't really lend themselves to running demos while one talks. Okay, so what classes of complexity are we really interested in? The answer is, although there are actually infinitely many of them, and computing scientists, especially in the States, love to spend a lot of time thinking about this, and all the infinitely many different kinds of algorithmic complexity classes there are. We're actually only interested in 4 of them, really, in practice, because beyond this, they become infeasible. So you'll see that all the algorithms that we commonly use in development, in all programming, are either constant time, order 1, which basically means that it doesn't matter how much data you have, they're always going to take the same amount of time. So then an example of that is calculating a hash code. A hash table under happy circumstances, if the loading is low, lookup and retrieval from a hash table takes the same amount of time, no matter how much data you've got there. Obviously, if you have a lot of data in there and the loading on the hash table becomes greater, then it isn't order 1. But that's your goal for a well-behaved hash table. Order log n is typically, that's for things like binary search. If you double the length of or say searching in a tree, if you double the amount of data say you're doing binary search in a sorted array, you double the amount of data you're going to require to have one more step in the algorithm. So it'll be increased by a constant, because you've got to do, if you double it, then you've got one more search to do. So order log n, if you double the data size for that, then you increase it by a constant. Order n is like linear search in an array, and then if you double the length of the array, or double the data size, then you're going to double the number of program steps there needs to be. That's kind of obvious, I think. And then there's n log n, which is obviously a kind of cross between these two, between n and n log n, and that is typically you typically need that for sorting. So sort algorithms typically take n log n, and if you double the data size there, then it's getting worse now. You not only do you double the not only do you double the number of execution steps, but you've also got to add an amount that's proportional to n as well. So it's kind of getting it's getting a bit tough. And beyond that, the next one after that, or the next common one after that, because there are many in between here, but the next common one after that is order n squared, which is things like bubble sort. If you double the size of the data there, well, you're going to multiply the number of program execution steps by 2 squared, which is by 4. So if all you need to do is double the data size a few times, and you're going to have an infeasible algorithm. And beyond that, they get worse and worse and worse. So order n cubed, for example, is just like nobody will ever write a program that's going to do any realistic work for that. Not really for order n squared either. So this is the idea of algorithmic complexity, and it was and is a big deal for understanding how programs work. I guess probably this is revision for nearly everybody, because you do this in your first year of a computing science course. But I never did a computing science course, so I had to learn it another way. Okay, so that's really all I'm going to say about this, except one way in which I found you should be using it. So this comes back to what I wrote in the book on generics and collections, and I discovered something through doing this. It's a really good way of discovering things, is to teach them or to write about them or something like that, and then you get put right in the mistakes you're making very quickly. So the person who put me right was another candidate for your father. Maybe you might have heard more of him, because he's actually really important in the Java world, and not active now, but very active for a while. Josh Bloch, author of Effective Java, which is like, for a while at least, and for many people still, was the text for Java in the same kind of way as the art of computer programming was for programming. So Josh was also the author of the Java Collections Framework. And so I was extremely lucky when I wrote the book on collections to have him as a technical reviewer. So that's like, you got royalty there. So, and I was hugely lucky, because I had a lot of things wrong in the book, and he fantastically detailed review. So transforming the book from something that would not have been good at all into something that was fairly reasonable. So. Or, as I like to say, the best book there is on generics, on Java generics. I know that. Never mind the collections part, it's the best book on Java generics. So you can probably figure out how I can be so sure that it's the best book. Hey. So one of the things that Josh told me, amongst the many things that he found wrong in what I'd written, and he was pretty merciless about pointing them out, one of the things he found he objected to was diagrams that I had in the book, like this, which you find in many books and you find in blog posts and so on, where people try to explain the Java Collections Framework in terms of the interfaces and in terms of the abstract classes. If you look inside java.util, there's a whole bunch of these abstract classes which are like starting points for implementations. So if you wanted to write your own Java util list, your own implementation of Java util list, you'd almost certainly start off with a Java util abstract list or Java util abstract sequential list, because it very conveniently does a lot of the stuff, does a lot of the busy work for you. That you would need to do anyway before you got onto the interesting stuff. And Josh said, don't do this. He said, client programs aren't a bit interested in these abstract lists, these abstract collections. Don't do that at all. What people want to know about are the interfaces. And they may actually want to know about the implementations, but they want to know about the implementations after they've found out about the interfaces. Because the interfaces tell you what functionality the collections are going to provide. Well, the collections framework has moved on a bit since 1998 when Josh wrote this and wrote it. And what he said then isn't quite as true as it was, but it's still a pretty good rule. And what he told me was, if the Java Collections Framework is interface-based, you should choose the interface that you want that reflects the functionality that your program is going to need. You know whether you want a set or a list, because you know whether or not your data structure is supposed to contain duplicates, or whether you need it to be ordered. Right? Sets can't contain duplicates. Lists can, and they are ordered. and you choose the interface according to those requirements, and then you choose the implementation of the interface with the best performance for the usage scenario that you have in mind. So the idea is that this is certainly something that I talked about in the book. The idea is that you, if you want a list, then you work out whether or not you're going to be spending a lot of time adding and removing elements from the beginning of the list. If you're going to do that, then in principle, array list is a bad idea. In practice, maybe a different matter. But in principle, it's a bad idea because every time you add or remove an element from the beginning of an array list, because array lists are always zero indexed, you're going to have to shuffle all the elements up or shuffle them down in the array. Now, if you're going to add or remove an element from the beginning of a linked list, then all you've got to do is just add a cell and swing the pointers a bit. Right? So it looks like adding and removing an element from the beginning of a linked list is order 1, it's constant time, whereas for an array list it's order n, because it's proportional to the number of those elements you've got to move up and down. Okay, so the constants maybe, I mean, that might be misleading because although the array list, adding and removing elements from the beginning of an array list is order n, the constant may come into it. So it may be order n, so that means it'll double, but if it was very small to start off with, then perhaps you don't care that much. And as it happens, moving elements within an array is an intrinsified operation, so it's very efficient. And possibly this isn't, we always have to modify these ideals with reality, but that's the principle. So that's the example of which array list which list implementation you would choose. It's kind of thin because, quite honestly, array list and linked list are the only real candidates in Java util, in the Java collections framework. Copy on write array list is quite specialized, so, and you'll see later on how real a choice that is. But anyway, I had tables like this in the book, and it says if you want to get an element randomly from an array list, then that's going to be order 1 because you've got random access. Whereas to get one from a linked list, from some arbitrary place in the middle of a linked list, the only way you can find it is by stepping along the list. So that's going to be order n. But on the other hand, removing an element from the beginning of a list is order n for an array list because you're going to have to shuffle all the elements down. But it's order 1 for a linked list because you just got to do a bit of pointer swinging. And so the idea was you look at the operations that your program is going to be performing, and depending on whether you've got more of these than these, or more of these than these, you choose one of these two, because you're going to go for the fastest operation for that. So a reasonable question is, did this ever make sense? Right? Because I'm already obviously quite doubtful about it. And the answer is, well, it did. Yes, it made some sense anyway, on some assumptions. First of all, you've got to be able to ignore the constant factors. So the constant factors will always be overweighed in the end by a higher algorithmic complexity. But in the end might mean really in the end. So you might need to have a huge array before moving the elements in it was more expensive than the pointer swinging that a linked list requires. That's a possibility. The assumption is that all instructions have the same duration, because it just gets too complicated if you're going to. I guess it'd be possible, but we know that in practice, machine code for the length of time a divide operation takes in native code is completely different and far more than what an addition takes, or bit shifting. So some are actually much faster than others. There's an assumption that memory doesn't matter, at least as far as this is concerned, but though there's a parallel idea about space complexity, but we were never really so interested in that as we were in as in time complexity. And importantly, that instruction execution dominates performance. So the only reason you'd be interested in the number of program execution steps you're taking, the only reason you'd be interested is because that's going to be the thing that will control how fast your program runs. If it turns out that it's something else that actually dominates, then why would we be spending all this time on that? So it's a reasonable question to ask whether complexity study ever was worth it. Well, actually, despite all of these things, it really was. Instruction execution sometimes really was the bottleneck. I mean, there are lots of others. I'll talk about. I will glance on these at various other times. But the thing that stops a program from things that may be the limiting factor on program performance, if you've got a slow disk, or you've got to get a lot of data over the network, then it doesn't matter how good your algorithm is. That will be the limiting factor. Similarly, if your garbage collector is badly tuned, or you're just creating an enormous amount of garbage so that that's the thing that's taking all the time. Again, the algorithm won't matter, and so on. Resource contention, and many other things as well. And there's this standard picture which everybody draws, which is that when you just think, oh, I'll get rid of this bottleneck because this is the bottleneck that's stopping the data flowing through my program. So you get rid of it, only to discover that there's actually a much worse there's a bottleneck further down that you hadn't noticed before, because that was the one that was restraining the flow, and possibly the extra pressure on this one will actually make your overall program performance worse. So I'm making sure that you have this idea of program efficiency in a context which is much larger than just what your program requires. So what to think about? Well, what to think about 3% of the time anyway. When we look at how a program is, assuming we're looking at a program that is executing slowly. Well, I'm going to take the 30,000 foot view, because that's to say that's an idiom in English which is about starting high up and taking an overview of a problem before we get to look at more of the detail, because I don't want you to think, I want to give you the idea that you should be focusing, even 3% of the time, you should be focusing on the one thing I'm talking about here. So I'm going to assume that that we've got a program we've got a system that's running slowly, and how we want to know what's going on. So there are lots of system monitoring tools in Linux in particular, because Linux is what we mostly think about. There also are in Windows, but they're not so good. And VMstat is a good starting point, which you've probably come across. So I'm just going to briefly put up a picture of what VMstat might look like. And these different sections of VMstat all represent, read properly, represent different kinds of problems in your system. So we're going to work our way across, and then I'm going to say, well, actually, we're only interested today. I only want to talk about this, but those others might be the problem at other times. So the procs are the number of that's the number of processes waiting in the run queue, or that are blocked in uninterruptible sleep. You can, for VMstat, you can ignore the first line, because the first line is an accumulation of everything that's happened since the startup, if you haven't run it before. Memory, okay, so there's a lot of stuff here. This is the number of, the amount of virtual memory used, the amount of memory that's free, the amount of memory in buffers, and the amount of memory used as a cache. If your program if there was something wrong with your program in other ways than what I want to talk about, this would be important information. This would be your starting point, really, for finding out what's going on. This is the data that's being, the amount of memory that's being swapped in and out from disk. This is the amount of I/O that's going on, and that typically from disk, from block-structured peripherals. This is the number of system interrupts there are, and the number of context switches. And this one is the CPU. Right? So, as it happens, I took this screenshot today from a system that was running one of the benchmarks I'm going to show you on that revealed a caching problem. So, like, maybe it's a kind of bad example, because this is the one that tells us that there's something wrong. For your real system, you want to look at all of these. You won't necessarily end up looking at this one, but this is the one we're going to look at here. Actually, it doesn't look too bad, because you think, well, there's, this is the amount of CPU time that's being spent in user space. This is the amount of time that's being, user space being the one we're really interested in, because the JVM runs in user space. This is the one that runs in system space. This is the amount that's idle, the percentage of the time that it's idle. So it looks like this is kind of idle about 50% of the time. What's ST? no, time, no, it doesn't matter. This is the time it spends waiting for I/O, and that's something that is new, and I don't care about it. So why would I be thinking that CPU usage was a problem here? Okay, well, I didn't tell you. I should have started off by dropping the key information into this onto this slide before I explained it. But if I tell you that it's a typical laptop, it's about 3 or 4 years old, an Ivy Bridge laptop, then you might be able to guess why I would be worried about this. It looks like it's spending about 50% of the time in user space and about 50% of the time idle. Any guesses? Why that might represent a problem? I'm not asking you, Kirk. I know you know. Okay, so this gives you more of a clue. Actually, does this give you more of a clue? Does this actually? No, it's still only giving you a clue. Percent idle. Okay, that looks all right. So now I've moved over to MPStat, which is something you would do if you knew you had a CPU problem with CPU usage. So there actually is there's a kind of broad clue on this slide as to why that 50%, which is actually really, well, it doesn't show it here actually. It's 60% and 60% and 59%, and we've got 33 here. Put that hand down. Okay, so I'm just running MPStat without distinguishing what's going on. I'm just saying I'm running it in the default zone. Okay, Kirk, tell them.
I have no idea what you've done here.
It doesn't matter, but you can.
All I know is
It's single-threaded, yes. Yeah.
single-threaded.
It is indeed single-thread, yes. Okay. So why are we still only getting the CPU is struggling? Why have I got all this idle time? I have got more than one core. I've got two cores. Yeah, that explains the 50%. So if I run it again, I say it doesn't look too bad. But if I run it again with listing the processors separately, with say I want to see the processors separately, then what I see is that processor 0, it's a 2-core machine. Processor 0 is running at 67% idle, and processor 1 is running 0% idle. It's maxed out. And that's the case all the way through. Well, that's the benchmark. I mean, it was designed to max out. But that actually means I've got a problem, and I'm going to want to think about what that problem is. So I'm just kind of taking you through these steps because I want to be sure that you don't think that that this is always going to be what I'm going to talk about today. It's always going to be the central problem for any program you have that isn't performing right. You have to try and work out. You've got to narrow the problem down, and in this case, I've narrowed it down, obviously very fast, to CPU usage. So, processor 1 is maxed out. Where do we go next? So here's a picture of where you want to go next. This is a mind map drawn by this has got, you can. I don't expect you to read this, obviously, but it's got CPU in the middle of it. So this is a mind map that was produced by Alexei Shipylev, who's a performance expert in. Sorry? Oh, okay, right. Okay, it was evolved by Alexei and friends. In fact, there's acknowledgements here. The credits here, which you also can't make out. So he gives credit to people for contributing to this, and the idea is that you're going to find out all the different things. This shows you the ways in which you tackle performance problems. And this one is, since I know you can't make it out, this one is sys. This one is IRQ and soft. This tells you what to do in the case of I/O wait. This tells you what to do in the case of idle. So these are headers on the MPStat table that was on the previous slide. And I'm not interested in these, but I just want you to know that again we're narrowing things down because we're only going to look at user, but if the user percentage is high. So that's what I'm focusing on here. And the particular things I want to look at are these here. And again, you still can't see it, but here you are. That's it zoomed in a bit. And you can see that I'm interested in algorithmic problems. Oh, well, lots of user space, algorithmic problems, and I've talked a bit about algorithmic complexity. So that's one possibility, right, in Alexei's mind map. The tool you use if you've got algorithmic complexity problems is your profiler and your brain. And he says, well, maybe what you need to do, if you've really got a bad algorithm, you need to change the algorithm. So that's one option. So another option, the other option I want to look at, now you can see there are many others as well. I'm not trying to hide from you that I'm only looking at one narrow problem, is memory problems and caches. So I'm going to look at what's labelled on this diagram as cache capacity. But I'm going to talk about other things besides cache capacity. I'm also going to talk about other problems you have. So what is this stuff about caches and capacity, or caches in particular? Why do we care about them? And that's what I'm going to go and talk about next. This can be a really major problem, and I'm going to take a look at why that is so. So that requires stepping back a bit in time to the way that computers used to work. So here's how computers used to work pre-1980. The way that I was brought up. This was my father's computer, as it were. My father didn't have a computer, but if he'd have had one, this would have been how it would have worked. So it was really straightforward. There was a CPU, and it retrieved data from memory, or got data from an input device. It got instructions from memory, and data from an input device. It did some work on it, and it produced some output. And that was the way I learned that computers worked, and I thought this really seemed pretty straightforward, and I didn't expect that it would ever change. I was massively wrong. I couldn't help, I'm afraid. The next slide is I just couldn't resist. I had to go, when I was looking for pictures for graphics about pre-1980 computers, I found pictures like this, which just, because I don't think anybody here, including Kirk, I guess, will ever have seen a machine hall. So we had these machine halls, which were big rooms. I mean, like, the one I remember in the first place I worked must have been maybe 1.5 times as wide as this room is long, and it was basically the size of a football field, much bigger than this one. And it was full of these cabinets and tape decks with tape reels that whirled around and so on. And of course, the power in one of these things, in one of these cabinets, one of these sets of cabinets was probably less than your mobile phone. I'm sure, much less than your mobile phone now. And I have to, and also something else I couldn't resist, though I'm sure I should have done, was the adverts that they used to use for advertising machines pre-1980s. You couldn't get away with this now. They always, for some reason, this is something called a mini computer, which wasn't the same as a mainframe. Again, it was a kind of mid-range machine. And they would always put them in a garden before they would take photographs of them. I don't know why. I mean, it's like this is an absolutely standard kind of picture for an advert for a mini computer. And there was always an essential accessory. They never didn't have a picture of a woman in, and usually, obviously, only as decoration. And I had to look for a while to find one that was decent enough to show. So this is like the most discreet one I could find. So why is any of this relevant? Well, to get back to complexity analysis, at the time that we're looking at those machines, RAM was phenomenally expensive by today's standards. It was in the 1970s, memory cost $1 per byte. Just imagine, just kind of compare that with the size of memory we expect to have now, and just think what would that would be. It's the GNP of a large country to buy a computer now, to buy a modern computer. And what happened in the decades since then is that the price of memory fell really dramatically like that. And that's got to be really great. And what it meant was for the usefulness of algorithmic complexity, it meant we went through a really golden time. Back here in the pre-1980. Memory was so expensive that you just couldn't afford very much of it, and so you'd have your data on disk most of the time. That was the only way you could have it. And so what would happen would be that although you could although obviously your processing took place in memory, you have to bring the data into memory to do the processing. The thing that dominated the execution of a program was disk speed. Because if the disk is slow, then that's going to be the thing that will really hold things up. So yes, it's kind of nice to have a fast algorithm doing what we used to call external sorting. External sorting is when you've got a data structure you want to sort, but you can't manage to get all of it into memory at once, and so you have to take it in bits, sort those bits, put them back out of the disk, get another bit in, sort that, put that out. Now bring chunks of the ones you've already sorted, but not the whole thing, into memory. So you spent a lot of time shuffling things backwards and forwards to disk, and that was what dominated. So as the cost of memory decreased, memory became cheap enough to execute algorithms in memory, and this is the golden age, what I've called the golden age of complexity analysis, and that was phenomenal and great for complexity analysts. And then something happened, and we lost the plot as far as that's concerned. So what happened? I mean, it's not that the price of memory didn't continue to go down, and in fact, it's not even that the performance of memory didn't go up. It went up really pretty well. I mean, in those 40 years, it went up by a factor of 10. These are logarithmic scales, of course. So what went wrong? Well, what went wrong was that although memory improved in performance like that, processor performance did something different. So processor performance increased phenomenally. So while memory was increasing by a factor of 10, the speed of memory was increasing by a factor of 10. The speed of the processor was increasing by a factor of 10,000. And what that meant was that the big problem is, how are you going to get enough data and instructions to the processors to keep them busy? Because now the memory bus is the limiting factor. So keeping the cores running today involves you having to what's usually called a pipeline, a data and instruction pipeline, which brings data up from data and instructions up from memory through a series of caches. These caches are typically the last level caches shared between the cores. And then you've got level 2 cache. I mean, not all processors, they don't all have 3 levels. So this isn't a diagram for all possible architectures, but this is pretty common. You've got level 2 cache, which is for per core, and you've got level 1. Very fast cache. So the reason for doing it in this way is because it's very useful to have a memory, what's always called a memory hierarchy, in which the memory that is nearest to the core is very fast. So the idea of that is that the core will be able to work with data. The data that it's got that it has close to hand it'll be able to access that, and typically only 3 or 4 times the length of time it takes to execute an instruction. Roughly speaking, these are. I've lost the. Oh no, it's on the next one. So roughly speaking, these the performance, the speed of data retrieval from each of these levels is about 3 or 4 times worse as you go down for each one. So this is about 3 or 4 times slower than an instruction. This is 3 or 4 times to retrieve data from here will typically be 3 or 4 times slower than that, and so on down to the memory. So eventually, when you get to memory, you're about something like about 200 or so times slower than, maybe more than that, slower than level 1 cache. So there's the memory hierarchy, and the things that vary are the speed and the power and the cost. The reason why we don't have a huge amount of level 1 cache is because it's very expensive, and because it takes a lot of power, and there's only so much space on a chip, and the hardware architects have to think really, really hard. I mean, they come up with different solutions, and sometimes they're successful, and sometimes they aren't, about how to get the best possible performance out of this. That's solving a problem in a multi-dimensional design space. Very difficult to understand. So sometimes, since on this MacBook Pro, the processor is about 3 gigahertz, I think. The a register to get the to get data from a register, or rather to a clock cycle, sorry. What I'm saying is a clock cycle is about 1/3 of a nanosecond then, if it's 3 gigahertz. Level 1 cache is 1 nanosecond, level 2 cache, 4 nanoseconds, so multiplied by 3, multiplied by 4. Level 3 is 16, main memory about 100. So since it takes only 100 nanoseconds to get data up from the physical memory up to the CPU, it's kind of quite hard for you to think. It's really hard to get an intuition of why it's such a bad idea to have to do that. So the way I like to explain this is I imagine a person standing at a cooker boiling eggs. And the reason I chose boiling eggs as the operation is because everybody knows how long it takes to boil an egg. It takes 3 minutes. So I'm going to turn this into like human terms. So as long as they can just pick an egg up and put it in the cooker, they can have a throughput of 1 egg every 3 minutes, and that's great. So imagine the eggs have to come from the refrigerator, which is the other side of the room, and the way that the caches work is the pipeline of data. It keeps the things moving. So my picture of this is actually I did actually find something that nicely showed it. This is a Mongolian stamp from 1977, showing the way that they put out fires in Mongolia. So presumably when they don't actually have any pipes or fire engines or something like that, if you've got to get water from the stream to the burning house, where you pass it hand over hand. So we've got a picture a little bit like that. The data is being passed hand over hand to get to the processor, and with the difference that these guys at this end are quite slow, and these guys right next to the house are much faster. But the problem is going to be that if something goes wrong, you have what they call a pipeline stall, and say, for example, the program takes an unexpected, the data is being loaded in anticipation of it being needed. And if the program makes an unexpected jump and that data isn't needed, everybody drops their bucket and the whole thing has to be loaded again. So there's a lot of eggs on the floor in the case of my kitchen analogy, but then they have to start again, bringing the eggs to you. Now if the retrieval time from memory is typically about 300 times a processor cycle, then if it took me 3 minutes to boil my egg, it's going to take me about 900 minutes for the new eggs to come from the refrigerator. 900 minutes, 15 hours, I think, roughly. So that's the length of time I'm going to be standing idle at the cooker, waiting for something to do. So you can see the cost of a pipeline miss, of a cache miss, and worse still, of a complete pipeline stall, is enormous in terms of lost opportunity for the processor. It's going to be sitting there twiddling its fingers for a very, very, very long time. And actually, if you think that's bad, just think of what it's like if you have to go to disk. I mean, that's like, instead of just getting the eggs out of the fridge, you have to go and get them from the shops. Right? So that's another 100 times, well, 1,000 times as long. So you're waiting literally years for the data to come in, for the eggs to come in. So cache effects often dominate. Main memory retrieval costs about 200 or 300 times register access. Typically, the hardware architects have spent a huge amount of time thinking really hard about how to make sure that caches work effectively. And the result is that typical programs have like 95% hit rate. And they're really ingenious. I mean, and they take into account lots and lots of different factors. It's much more complicated than anything we do. And the results have been pretty successful. So that's a good number, but that 5% really hurts, and it can make a huge difference. If it goes up from 5% to 10%, you're really going to notice the difference in your program. So why do we get cache misses? Well, two possible reasons. There are many others, and I'm not going to talk about all of those because many of them are hardware related. So most of the things you can do to get the you can do to improve or to eliminate cache misses and to improve cache performance, the big majority of them are actually what hardware architects can do or have to do. So they change the size of the cache, they change the size of a cache line, which is the unit of the cache. They give reads priority over writes. They arrange the kind of access there is to the caches differently. They divide them into separate banks. There's a whole lot of stuff that they do. The standard textbook on computer architecture, hardware computer architecture, has 16 different optimizations for what that can be done to try to improve cache performance, and 14 of those are hardware related, and you can't do anything about them. So what is it that you can do? Well, the things that matter to us as software programmers are we may be able to, we may or may not be able to do something about the capacity of the cache. I'll talk about that, because we may be able to optimize our data so that we don't need so much cache. Obviously, we can't change the capacity that it has, but we may be able to change how we use it. And we may be able to do something about the prefetching. So prefetching is the anticipation that the processor makes, where it guesses what data or instructions you're going to want next, and it's really critical to get that right. And if that fails, then you'll really see an impact on your performance. And the reason that might fail is, for example, branch misprediction. So branch misprediction is when the processor says, or when the system can see that every time you've come to this particular branch in the past, you've always gone the same way. So you've got an iteration of you've iterated over a loop 10,000 times or 20,000 times, and the best guess is that you're going to continue iterating over it, because you're only going to there's only going to be a misprediction once in that case, which is the time that you leave the loop. So obviously the thing to do is to guess that you're going to continue in the loop. But branch mispredictions do cost, because that can produce an instruction or a data pipeline stall. And another possibility is you might get poor locality. So locality is temporal locality. Something that Kirk said to me during the break is quite important, actually. So we'll come across this again, but it actually it might be actually worth just mentioning it. And now, so he was talking about this slide, or at least I'd like to talk about this. Right? No, it's okay. I'm getting there. It's fair enough. See this? See how the processor speed? See, I've talked about performance here. That's not actually strictly true. I guess a lot of people know that around about 2003, processor speed flattened out. So we got to 3 gigahertz, and we're not moving much. We're not moving much from there at all. And that's what this is. And that has led to predictions about multi-core becoming a lot more important, since processor speed can't go up. But Kirk's point is that although the processor speed has flattened out, that actually there are things that the processors can do that actually enable them to do this stuff that I was talking about, to effectively increase their speed, for example, by more effective use of cache, for example, which has actually let them carry on improving. And I'm actually going to talk about that. The reason I'm happy to mention it is because I'm going to say that the results that you get in this area are very deceptive. So I'm going to be talking a lot about cache misses, but in fact, cache misses are not the thing that really decides for example, a cache miss in the pipeline stall doesn't necessarily mean that a loss of performance for the processor. It may be able to do other clever things in order to keep itself busy while the data comes up from main memory. So that's actually connected to that point, and I think it's probably worth mentioning here. So, right, so I was talking about about how cache effects dominate. Down. Still on the stupid thing, right? Okay, so we're thinking about the caches and how they work. Let me talk for a moment about prefetching. So we've got here. This picture is the processor with some cache lines. So typically you've got cache lines. These are the units of cache. For level 1, they're typically 64 bytes. So it's a chunk of memory, or a chunk of storage, which is 64 bytes, and you'll never replace individual values in it. If data has to be retrieved from memory to be placed in the cache, it's going to be brought in 64 bytes at a time. And if one element of a cache is altered and it has to be written back to memory, all 64 bytes will go back. Right? You can't. That's the unit that it operates in. So the idea of prefetching, of stride prefetching, is pretty straightforward. I mean, the best stride is a stride of 1. Like this, the processor can see that you're just iterating across an array, and then it can guess. And in advance of you needing it, it can say, "Hey, this is the next element that's going to be required," and so it can put that so it can get that into the pipeline. I've only drawn the level 1 cache here, but of course it would. It might well be reproduced also in level 2 and level 3. So actually maintaining that regularity of access is very important for the cache to work. What we typically do, if you think about how object-oriented programs work, typically what's happening is we're dealing with pointers all the time. So you create an object here, and then you create some other object here, and you put a reference to this one in there, and it could be anywhere in the memory. So our programs spend an awful lot of time following pointers. These data-dependent loads are really obviously each one of these is going to require a complete cache load, and it's actually a bit worse than that. And I might as well tell you quite how bad this issue of data locality is, because there's also the issue of the translation buffer, and sometimes called the translation buffer and sometimes called the translation look-aside buffer, for reasons I don't know. Memory is divided into pages, typically 4K pages, and the processor deals in terms of virtual addresses. So it has an index to a page. The way it thinks about a location in memory is it has an index to a page and it has the offset within the page. The major reason, there are many reasons why this is usual. The one reason that's kind of that will immediately make sense to you is to say that there's a security aspect to it. Security and stability, because the page index tells the processor which process the page belongs to, and so it's a really easy way of ensuring if processors can only ever write into their own page, the processors own a whole number of pages, then it's pretty straightforward for the processor to ensure that no process ever writes into the memory that belongs to another process, and that's such a key issue for system stability that it's worth paying a lot for it. So the processor deals in terms of virtual addresses, but the cache and of course the memory itself deal in absolute addresses. So how is that translation going to be done? The page index has got to be translated into a physical address in memory. So there's got to be a table to do that. That's the page table. The page table sits in memory, but it can be really big. And of course, if every time you wanted to translate a virtual address into an absolute address, if you had to retrieve the page table from memory to do that translation, well, that's another set of eggs you've got to bring from the fridge. So you've got a cache for the page table as well. And this is called the translation buffer, or the translation look-aside buffer. So this cache, which is not all that big, typically it's not enormous. maps the page index to an address for the page, and of course now you've got another cache here. So if your data dependent loads, the ones I was talking about here, jump over page boundaries, then for each one of those you've got not only to refresh the cache for the data and for the instructions, but you've also got to refresh. You may have to refresh the cache for the translation buffer if you've gone onto a page that you haven't previously been on before. So you're paying a double penalty for data dependent loads, and of course we do them all the time. We do them all the time. So this is actually a pretty major limitation on. It's a problem with object-oriented programs generally, but it's a problem that software architects actually, system architects, say for the Java architects, spend a lot of time worrying about this because it's a limitation on how well object-oriented programs, in particular the Java, can execute. So what I want to talk about next is I want to actually look at a couple of case studies for this, and I want to actually see if we can work out whether how the performance of tiny programs is actually affected by caching effects. I want to actually see them in action. That's not so easy because, of course, you're trying to work out what's going on in a phenomenally complicated system. You're trying to isolate a particular element of the performance. And so measuring caching effects isn't that straightforward. Kind of fortunately, modern CPUs have got these hardware counters to monitor events. You might remember from Alexei's mind map a little while back. He said, well, you're going to use HWC. That's what I put in there. You're going to use these hardware counters to monitor the events that happen to the hardware. Of course, you've got to read the values in these counters, and that's not completely simple because there are very few counters and there are a lot of events. Tools that can read these counters include some very fancy profilers like vTune, Intel vTune, which can tell you for your program how many of the different kinds of events have happened. And here, the kind of events I'm talking about are cache misses. And also the length of time that cache misses cost in terms of the processor performance. There's Oracle Developer Studio Performance Analyzer, which personally I haven't used, but which I'm told is very good. And I know that Intel vTune costs money, but I think the Developer Studio Performance Analyzer is free. Is that right, Kirk? It's proprietary software, but I believe it's free. A Unix perf is a tiny C program. Well, not a tiny C program. It's quite a meaty C program, which will read the performance counters for you. So there are different ways of going about this, and I've tried some and had difficulties with others. The problem with the fancy profilers is that typically what you're wanting to do. Well, if you want to find out what is happening in the system as a whole, then these are good. I think in different ways. But what I'm particularly interested here in this thing about collections that I want to explore and how caching has affected the complexity calculations for collections means I want to do micro benchmarking. And micro benchmarking is quite tough to do it's tough to do for any dynamic runtime, and particularly for the JVM. Micro benchmarking Java algorithms presents some special problems, mainly because the JVM is so fantastically good at optimizing your code. So people frequently make a lot of mistakes. Most micro benchmarks that you see aren't great because they don't allow for all the things that the JVM does to your code. The JVM does not execute your code the way you think it is at all, because it's making many optimizations. In the middle of doing your benchmark, the JIT compiler may kick in, and your code will be compiled from bytecode to native code. Numerous optimizations will then be applied, which there are literally dozens. But some that you might recognize are that it'll do method inlining, it'll take the code for a method, it'll remove the method call and just inline the code. It'll unroll loops. It will take operations out of a loop into the outer code in order to have to avoid doing them repetitively. It'll replace objects with the equivalent primitives if it can see that that's possible using escape analysis typically, and it will do dead code elimination. Dead code elimination is absolutely my favorite. It's very, very hard. This is a very hard optimization to circumvent if you were writing a micro benchmark. Why is it so hard to circumvent? Well, if you want to calculate, supposing, for example, you want to, I don't know, you want to iterate over a loop. You're going to do some calculation. What are you going to do with the results of this calculation? Well, if you don't do anything with the results of the calculation, then the compiler is going to see, hey, you've not done anything with that, and it will optimize that code away. If you do something with the results of that optimization, then typically what you'll do is say, I'm going to print this out to the console. And then printing things out to the console is such an expensive thing to do that that will now come to completely dominate your measurements. So actually working out how to fool the compiler into thinking that you need results, while at the same time not actually using them in an expensive way, is pretty tough to do. And so I'm always recommending that you use a framework where people have solved this problem. The way that particular problem is solved by the frameworks is that every so often when a value is calculated, it does something with it, but it does it very rarely. But not regularly, so the compiler can't figure out that it doesn't need to calculate the value because it doesn't know whether it'll be required. And that kind of thing is really tough to get right. So you can't do that and your day job as well, basically. You have to leave that sort of thing really needs the experts. And there are other things as well. Sometimes your code can get de-optimized after it's been optimized. So for example, if the compiler can tell that you've only got one subclass of a superclass loaded, then it knows that although in principle it should use virtual dispatch for polymorphic call, in practice there's only one method they can go to. It doesn't need a jump table. But then if another subclass gets loaded, then hey, we better back out of that optimization and we better go back to proper polymorphic dispatch. So that kind of thing as well. It's going to screw your results up if that happens in the middle of your benchmark. Garbage collection, of course, can always happen. There's a lot goes on, and eliminating all this stuff from your micro benchmark, so you're focusing just on the thing you're interested in, very hard. So the answer is always to use a micro benchmarking library. I'll just stand in front of this because it belongs at the bottom of the slide. So micro benchmarking libraries. I mean, Google Caliper I always used to quote as one of them, but I never used it. The one that is most important, I think, is the Java benchmarking harness, which is now part of the OpenJDK. Also written by Alexei Shipolev, well, obviously with help, but originated by him. So why we're especially interested, you should be interested in this anyway if you ever want to do any micro benchmarking. So it's a fantastic piece of software. But what we're especially interested in here is that it can work with perf, Unix perf. And Unix perf can actually monitor the hardware events, so that if you put these together, you can actually see what's going on, and that's what I'm going to do in the next little bit of the talk. It actually JMH also has an option, perf asm. Perf asm. No, somebody said this is so good it should be pronounced perf awesome. Which will let you see which will actually let you see the native code hotspots, because it will actually tie back the perf events, the hardware events, to the native code that's been generated by the JVM. So finally, we get to the slide at the bottom. So here's an example of using JMH with perf. And here what we're doing, sorry, I've just seen a note which told me I should have done that. I should have done a demo of some kind. I'm trying to remember what demo I was supposed to. Oh, I know what I'm supposed to be doing. Yes, so I'll just finish the sentence. So here what we're doing is we're running a jar here which has been generated by the JMH framework. So what's special about that? Why we're running that jar? Because it does bytecode weaving. It does all kinds of things in order to ensure that code that you generate is actually going to say, for example, if we say we've got a black hole, there's a black hole annotation that JMH uses, and what it'll do is it'll weave bytecode, which will do that clever trick that I talked about losing your result just some of the time. And here I'm saying at the bottom here, I guess not everybody can see this, that this is the profiler I want to use, and these are the events I want to find. In this case, I want to find the L1 requests that are missed, level 1 cache requests that are missed, and the level 1 cache references that there are. And those event requirements will be passed through to perf, and JMH will give them back to us in the results. I remembered what the demo was that I was supposed to do. I put it in huge letters. Don't forget to do this demo, and then didn't read the huge letters. So it's not really a demo. I just want to show you what JMH code looks like. If I can find this, that's the wrong one. Let me find the right one. Right. Okay. So I'm not going to talk about this. I don't want to talk about this in a lot of detail. I mean, there's obviously far too much to. Learning about how to use JMH takes considerable amount of time in itself, but I'll just mention what some of these things are. You can see that the code doesn't look much like ordinary code. The things that we're actually benchmarking here, the methods that we're benchmarking, have an annotation on them that says it's a benchmark. So this is a benchmark, and this is the mode it's operating in, and we're working out how many that we want operations per invocation. And you can see that actually that even though it's not returning a result, JMH knows, because it's a benchmark, it knows that it's going to profile that, and evades a lot of the problems that I talked about earlier. We've got within this code, there are different ways of running JMH. This is only one way, but I just want to give you a feel, if you haven't seen it before, of the kind of thing you can do. Here I'm saying that I want to, I'm going to run this repeatedly with the length in K, which is going to be the length of a list that I'm going to benchmark, and I'm going to run it for each one of the different list structures here. I'm going to run it first of all with one element in, then with 7, then with 63, then with 511,000 elements each time. What else? You can see that I'm measuring I can specify I can configure how JMH is going to behave from these annotations here. Very importantly, I can say that I want to warm up, because the first results that you get when you run a program are typically not very meaningful, because there's all kinds of warm-up effects. Cache is required to be filled, just-in-time compilation needs to take place, and so on. So the first results aren't very much used. And then we're going to iterate for 10 times and so on. I'm not running this in this talk, because it takes far too long to run any reasonable benchmark that doesn't work in the talk. But I'll show you the results of running an earlier version of this. But I just thought you should have some sort of feel of what JMH code is going to look like. And it's not. It's really it takes some getting used to writing, yeah, for sure. Okay, so how does caching complicate complexity then? Well, let's have a look at. I'm going to look at a couple of issues. I'm going to look at cache capacity, and I'm going to look at data locality. Sample case is going to be traversing a list. Traversing a list is obviously order n. Right? It's just linear traversing of a list, and I'm going to compare a linked list with a primitive array. You might wonder, why am I going to compare a linked list with a primitive array when linked list isn't that great a data structure, and array list would obviously be better. But you'll see that, in fact, it wouldn't make a great deal of difference to the problem I'm seeing. So for linked list, here's the results. As I said, we're going to iterate over a list in 4 different cases with 1K, 763, and 511K. The cache, in this case, the level 1 cache was 32K. It wasn't on this machine. It was on a slightly older MacBook Pro. Performance. Right, so the performance here is the number of nanoseconds per operation. Operation is an iteration on the list, a single step on the list. And you can see that it's got massively worse here. Right, so order n is just not holding. We've got a factor of nearly four, no, more than 4, between the 1K and the 511K. So see if we can figure out what's going on. So the CPI has got worse in pretty much the same kind of way. What's the CPI? So the CPI is the number of cycles per instruction. So you might think, well, number of cycles per instruction should surely be 1. Right? I mean, that seems like that kind of makes sense. But what we're talking about here for most modern architectures are what are called multi-issue architectures. So the idea is that you can get several instructions are going to be being executed by the processor at the same time, because each instruction is in a series of stages. It's got to be broken down into the micro operation, and the data's got to be loaded, and there are 4 or 5 different stages, and the processor is capable of doing one of these stages at once. But what that means is that it can do them in parallel. Sorry, it can do one of these stages for each of a number of different instructions in parallel. So I meant to put a diagram on this, but I forgot to do it. So in practice, at any given time, for a multi-issue processor, you can have many instructions in the course of execution at different stages in their execution. So actually, CPI of 1 is pretty bad. And you can see this starts off pretty good, and it goes pretty bad. It's actually pretty much in line with the decrease in the performance. If we turn to looking at the events per operation, we see that the number of machine cycles, you'd expect actually these two are going to be pretty much tallied. The number of machine cycles per iteration, per step in the iteration is going up. Actually, that's gone up significantly worse than even the performance has. But the number of instructions, the number of instructions per operation has stayed the same. So, right, so this is the evidence, if you ever needed any, that algorithmic complexity isn't. There are going to be times when it's just not going to be a great proxy for program performance. Performance has got hugely worse, and yet the number of instructions executed, the basis for how algorithmic complexity works, is just pretty much constant. In fact, decreased very slightly. So what's going on? So that, I think that's a pretty significant figure. So what's going on here? Well, we can look at the caches, and Perf will allow us to look at the caches, and you can see that the L1 data cache load misses has gone up from 1.18, which is okay. So that's one miss per operation to 2.65. So that's a significant increase. And remember what I said, that a small increase in that 5%, if that 5% goes up to 10%, then that's going to make a huge difference to your performance, and that is what's going on here. And for the rest of it, well, we see that the number of loads is pretty much the same. It's the number of misses compared to the number of loads. You can see, in fact, that the percentage is still pretty small. It's still only 10%. In fact, it's done just what I said. I didn't realise this, but you remember I said it was 5%. Typically, 5% for a program. It's gone up to 10%. Huge difference in the performance. The last level cache is the one that's nearest to the memory, and that too has started to go up here as well. So overall, you can see that I can't be certain that the difference in the performance is due entirely to this caching problem, but it certainly fits. Kirk thinks I can be sure. Yeah. And you see even that the translation look-aside buffer has started to miss as well. That's the one that's the cache for the page table. So things are pretty bad. So that's linked list. what's going on here is, well, for a linked list, the node size is 24 bytes. The new list item, so the cost in memory of each new list item is going to be 24 bytes plus 16 for the integer. I've got a linked list of integers here. so if the level 1 cache is only 32K, then it's pretty clear I'm going to blow that at less than 1,000 items, because 1,000 items will cost 40K. So all subsequent iterations are going to have to they're going to be what they call capacity misses. The cache just isn't big enough. We're just going to have to reload the cache every time. And so the reason why I stuck with a linked list instead of going to array list, because that should be better in principle, it's not actually going to show much better behavior. Not, in fact, because array list is a bad data structure, but because each new element of an array list costs, well, of course, you don't have this overhead. You don't have to create a new object when you're creating a new element on an array list. All you have to do is allocate one more reference on an array of references, right? So it's only 4 bytes for that. Amortized over, because the array list grows bigger and bigger, and so, but overall it averages out at 4 bytes for the reference. But you're still going to have to pay another 16 bytes for the integer object, and so each new element's going to cost 20 bytes. So effectively, you're not actually that much better off. Well, yeah, you can get twice as big a list before the cache is blown, but it's still not very big. Let's do the same thing with a primitive array, and you see a huge difference. This time, because a primitive array, of course, doesn't have that overhead of the object header, and the integer, the integer which takes up what is it, 16 bytes, now only takes up 4 bytes for a primitive array, because it's just the number, and we see that things look quite different. So the instructions stay the same. The level 1 misses are hardly move. The last level cache doesn't miss at all, and the performance is linear. It really is. Really is. So I mean that's actually, I think, pretty compelling evidence for the proposition that cache behavior is going to make a really big difference, and it's going to make a big difference for you as for your collections, thinking about what collections there are. Now, here's another thing that I regret about the Java 5 book. We wrote in that arrays were essentially legacy data structures. There's nothing that you can do. There's nothing that you can do with an array that you can't do better with a collection. And in functional terms, that is true. But in performance terms, 3% of the time, then you may need to modify that opinion. I certainly have done. Second issue. Okay, so that's the first issue. Then is just cache capacity. Second issue, data locality. So there's different problems here that I'm going to talk about. The data density is how much of your 64-byte cache line is data that you actually need. Because remember, the cache line has to be replaced as a whole. So if in fact you're only interested in one byte of that, you're still going to have the overhead of loading an entire cache line for that and storing it when it's changed. And of course prefetching, which I talked about earlier. I ran a little experiment to show the effect of prefetching on populating on a linked list. So the way I did this was I populated the linked list. I like to say naturally, but that's just my word for it. So basically, what I'm doing is I'm just adding new nodes to the list. The green things are integers, and the blue things are linked list nodes. And if I write code like this, they'll tend to get allocated contiguously. That means all joined together. So you should get relatively good data locality there. And to compare that, I did something different. First of all, I created an array list, And I sequentially allocated each one of the elements to a new integer. So again, I was expecting these to be pretty much contiguous. But when I came to populate the linked list, I chose random. I did so choosing random elements from the array list. So the first one pointed to here, and the second one pointed to there, and so on, backwards and forwards in there. So the idea was to get really bad locality, just to see what would happen. And here's here's the nearest I could get to running a demo of a JMH benchmark in a talk, because like you can't do it. It takes like 5 minutes or 10 minutes, even for this tiny one. So I recorded it and speeded it up, just so that you could see the kind of thing that would happen. So here it is at work, and meanwhile I have to kind of do something, I don't know, juggle or something. Well, while it's going on. I suppose what I could say is you might think that all this is completely academic, but I don't think that it is, actually. I think if you have this understanding, then I think there are options, or there are times when there's opportunities to organize your data with locality in mind. So I think, for example, if you have data that you know isn't going to be changed a lot, but it's been generated in a way that doesn't have locality, then you're going to have to traverse it and do many read operations on it. It might well be worthwhile paying the cost of a big reorganization and bringing it into contiguous form. So there's the difference between those two runs, and it's, you know, that's just data locality that got that difference. There was nothing else involved at all there. So again, you see the caching effect's pretty significant. So linked list, poor unloved linked list. So Josh wrote it, but not even he loves it. It's really a widely reviled data structure. So everything I said at the beginning about how you would choose an array list, linked list, probably really wasn't very true. So that's kind of most of what I want to say, and we're coming to the end anyway. I'd like to do a lot more work. There's a lot more work waiting to be done in this. For example, something I'd like to look at would be better hash maps. So you tend to think, if you're going on order n, on algorithmic complexity, then you may well think that the problem with a hash map is going to be collisions. Right? When you get a heavily loaded map, then what happens is new elements come in, and they're going to have the same hash map as one they previously had, and so what's going to happen is, I mean, this is the way it's meant to work, where you have different buckets are being used by different elements. But another way in which it can work is to have the same bucket used, and then you get overflow. So in pre-Java 8, you would get a linked list here. So in the worst case, it could deteriorate to linear performance, and even in Java 8, you go binary tree under many circumstances. So you think, well, that's a bad thing, and really what I should be doing is trying to ensure that, I mean, it's still a good rule to say, well, what I should be ensuring is I've got an even spread of hash codes so that I don't get a lot of this overflow. But with the insight that I've tried to convey in this talk, you'll see that actually, even when it works well, you've still got poor data locality with this. Even when you've only got a chain of one element. Obviously, it's worse if you've got multiple elements, but it's still not great. So one possibility, something that is worth thinking about, and I haven't investigated this, but I'd like to, is the idea of, well, I mean, there are various possibilities. I mean, the simplest one would be what's called open addressing, and confusingly called closed hashing. So the idea of that is that you take these two parts, the node part here of what a hash map has, and you actually put it into the array. That's open addressing. And what that means is that you're going to get you're going to get much better data locality, at least for these parts. You're still going to get pointers to the data, but at least to the key and the value. But the pointers to them won't be in a separate data structure. It'll be in there. So that would improve your data locality a bit. There's always a trade-off in these things. Open addressing maps perform very, very much worse when there's when they're heavily loaded. So because you've got to search down the bucket array looking for the right key value pair pointers, or rather for the right key, they're liable to perform much worse. It's just I mean, there are just no good answers. If there were, we'd be using them already. There's no. I mean, when I say there are no good answers, there's no kind of magic cure for these problems. Right, immutable collections. Immutable collection, I thought there was a diagram like this somewhere. These immutable collections are in Java 9. They're the ones that you get by saying, yes, good. They're the ones that you get by saying map.of entries, for example, and they do exactly this. They do have the key and value pairs are in the array. But of course, they're immutable. Right? So this is an example of a place where I think you might do well if you'd created a large map and now you're worried about its behavior in respect to caching. It might, but it's not going to be changed anymore. It might well be worthwhile copying it into this data structure and taking the cost as a one-off hit, which will be amortized over lots of subsequent behavior. And of course, if you do something like this, you may be lucky and you may actually get the data to be contiguous as well. So, third-party collection frameworks. I mean, there's a lot of work to be done on this. Third-party collection frameworks always boast about having low memory footprint. Every time I give this talk, somebody comes up to me and says, hey, there's this really good framework that you didn't mention. So there's a lot of these, and I would like to. The only one I've looked at all is Eclipse collections. You might have noticed that was in the benchmark earlier on. And there's a lot of others, and the fact that they have low memory footprint doesn't necessarily mean that they're behaving well with respect to caching. Those two things don't necessarily go together, but you're likely to be better off. And certainly, even though I've never seen I know the Eclipse collections authors, and they've never mentioned caching behavior, but they go on a lot about low memory footprint. And certainly, from what I've seen, from the preliminary experiments I've done, they are much better about caching behavior. Improving data locality. Well, if you really want to improve it, then you want something like object layout. So object layout is a separate library. This is created by Martin Thompson and Gil Tenney. These are people who are they're kind of giants in the area. And the idea of this is it's basically going to be it sort of does that thing I was talking about, which is that compilers sometimes do, which is what's the word? Scalar transformation, I think. So it takes the idea is that instead of organizing your data in objects, what it'll do is it'll actually put them into an array, essentially put them into a static array. So it'll be like, so the data's in an array, and of course it's going to be immutable then. You can't, you're going to lose a lot of the features that objects give you, but it will be much more efficient. And it also allows you to have arrays as part of objects as well. So it's basically sort of reverting to C. Yeah, because like that turns out some things about that were actually quite a good idea 20 years or 40 years ago. Other stuff that people have told me about, I haven't actually looked at this, is roaring bitmaps, which you can imagine, if it's based on compressed bitmaps, is going to be good. I mean, that's a good design decision if you care about performance straight away, or at least if you care about caching performance. Project Valhalla in the distant future is going to be a big deal for this stuff. This is you may have heard of Project Valhalla. This is this is the Java, the JDK architects' solution to or partial solution to the problem that I've been talking about. What they want to do is they want to create objects which will actually behave. They will be automatically scalarized. They'll look like objects, and they will, in most respects, and they won't subvert the semantics of the language, except in some particular ways. Like they won't have identity, but otherwise they will behave like objects. but the compiler will know that, that in fact you can store them as their primitive values. So they're going to, I think the slogan is something like compiles like an object, performs like a primitive. Pardon? Does Groovy do that? But does it do it? But does it do it as a primitive? Yeah. Right. Right. Okay. So yeah. So they got there with this, but this is going to be a general solution to that problem, which is like it's a huge project. So, but that's definitely going to happen. We used to say it was going to be in JDK 11, but of course we don't really know. Depending on what the numbering system is, it might be JDK 111. I don't know. But I mean, I think they're making good technical progress on that. It also involves other things as well. So it's going to involve, for example, collections of primitives and generification over primitives as well. So there's a lot of work to be done there. So the conclusion, well, there isn't really a conclusion to this. Performance only matters 3% of the time. Well, but when it matters, that 3% is really important. Every performance improvement obviously represents a trade-off. Algorithmic complexity is still important, whatever I've said today. But so are all these other things as well, most of which I haven't talked about at all. But the one that I have talked about is caching, and that really does matter. So it turns out that it actually really is your farthest complexity still. It's just more complicated than it used to be. Thank you for your attention at the end of a long day. Okay. So we've got 5 minutes for questions if anybody wants questions, but my feelings won't be hurt if you don't have any. Yeah, okay.
How much do those performance profiling tools apply to
So I think that the problems that we've been talking about here are problems of the JVM. So I think the answer is just as much. I don't know what it is that Groovy's doing in this respect. I mean, if you had an array of, could you have like a collection of primitives in Groovy?
Yeah, you can, but Groovy basically says everything is object. We'll do away with all primitives.
Right. The way we felt Java should have done. Yes, yeah.
You define a range, for instance. It's from 1 to 10. You behave like an object.
Right.
But in memory, it only remembers the 1 and the 10.
Right. Okay, so right. So we'd have to look at that in a lot more detail to know exactly how that was going to be affected. I think in general, this problem of data locality and the problem of cache capacity and so on is going to be the same for every language. I mean, for the JVM is executing on. But the biggest single problem for sure is data-dependent loads. That's the one that we can do most about. And any language that manages to reduce that, which possibly some of them can do, then I mean that would be something to look out for if you care about this. Yeah.
To explain, my intuitive sense is always that the caches on the CPUs were one of the most important things considered when you find hardware, but I never quite could prove it or knew for sure. But it seems like, in terms of real work, real world enterprise type apps, it seems like that is much more important than CPU speed. So I was wondering if that's what you suggest in terms of purchasing. I mean, not new ways of programming in terms of hardware.
Yeah, the problem. I think that's a good intuition, but the problem is it's just really hard to work out. I mean, the way that the improvement that caches give you depends on their size, obviously, how many of them there are, what associativity scheme there is for them, which is something I haven't talked about at all, whether or not they favor reads over writes, and what strategy they use for that. And there's a long list. I told you, Hennessy and Patterson has 16 optimizations. And for you to work it out is really hard. So I think probably the best thing to do I mean, I'm kind of reluctant to say this because I don't believe in them much, but if you really care about performance, it's probably to look at the standard industry benchmarks. I mean, I've just stayed clear of all of that because I'm just looking at micro benchmarking. I know where I am, but the standard industry benchmarks should reflect overall performance, and that's really what you care about. I mean, you see, even what I said. I mean, I've told you that cache misses are a huge problem, but I kind of lied about that as well. I mean, I told you the truth about that graph. One of the reasons, for example, that VTune doesn't report raw cache misses. I mean, you can make it report raw cache misses, but it doesn't. But they process the results into something you're meant to be able to understand, and they don't report raw cache misses because they figure that quite a lot of the time the processor can be doing useful work. In the case of a pipeline stall, so even the misses themselves don't tell you enough. Unfortunately, in the end, there's this really boring thing that performance experts say, which is like really painful, but it's true, and that is the only really meaningful benchmark is your application. Sorry about that. Okay, thank you very much.